All right. So now you are familiar with the concept of probability, and we really want to do something nice with that probability. So, what can we bring out? Look at something here. The topic today is going to be function of a random variable. Now, so function of a random variable, probability mass function, probability density function, and cumulative distribution function are the things we are going to be talking about. And so, what are we trying to do? We are used to the theoretical probability, uh, or also known as the classical probability type, where I come and say, okay, if I toss a coin, a fair coin once, I'm going to have a sample space uh, where S is going to be equal to head, comma, tail. All right, and somehow, we already know that a random variable looks something like this. Maybe x, for instance, can take values 0, 1, perhaps, and then we have the range space of x rather than x itself here. The range space of x will be, if x is the random variable, and we're concerned about perhaps the number of tails that show up, we may have something like range space of x equals to what we have on the board. But then we may also now come and say, okay, the probability is going to be something like maybe probability of x, for instance, x now is going to be something like 1 over 2, 1 over 2, 1 over 2. Yes, we know all of this, but well, when the work gets somewhat, we have a few number of elements in the sample space at this time, just a head and a tail. But what about if we have, let's say, 500, 200, 1,000, 1 million possible outcomes? How are we going to characterize that? How are we going to write? So it means that we have to write all the 1 million outcomes if we are trying to do that, and perhaps write all the 1 million range spaces and then the 1 million probabilities. All right, that's going to be very, very boring, and I don't think anybody's going to do that because you're not going to finish it. But what if we decide to find a mathematical formula that could give us all of this? So somehow we know that, okay, well, we may not be able to write all the possible outcomes, but somewhat we can have it covered in our formula, and we can also have all the possible probabilities, the corresponding probabilities to these outcomes, the corresponding probabilities, okay, and we can have them covered up in a formula. And what's that formula going to be? Now, it means that we need to find a way to go about this. All right, let's look at this more closely. So looking at this more closely, we are talking about, for instance, we need we need all of that, but there is a need to understand that apart from writing what we have written this way, all that we have written here this way, yeah, it looks good anyway, but we could write it in a much more better way. So supposing I say, okay, x can take values, and then we can have a probability for x. Then I put my 0 here, put my 1 here, then I put 1 over 2, 1 over 2. Now, this is a tabular representation of what I had before. So this is good as a tabular representation, but as I said before, it's not still the best. So there are other ways. Okay, there is another way that we can put it. That's using a mathematical formula. That's what takes us to the concept of what we call probability density function, and also what we call the cumulative distribution function. So we have all of these that is in the table now. We have all of this covered up in a formula. So each time we need the probability value of a particular figure, say maybe 0 here, we can get it to be half, but we don't need to know this in our head like the way we have put this one, committed this one to memory. So we just need to substitute 0 into that formula, then we get half. All right, so the probability density function in a nutshell is, I think I'll have it right here. Okay, let's just define probability function first. A probability function is a mathematical expression that gives the corresponding probability for each possible outcome of a random experiment. So that's it. Okay. All right, I think I need to let this go so the board can be freer. All right, now so a probability function is a mathematical expression that gives, okay, yeah, make it 24. This may be better. All right. So a probability function is a mathematical expression that gives the corresponding probability for each possible outcome of a random experiment. Now that's that for probability function. Now a probability density function, we're going to define that now. A probability density function is the probability function for a continuous random variable where the random variable, okay, continuous random variable, say x, where x takes values, okay, x takes values within, okay, we could just say where x is an interval. X is an interval. All right. Now, yeah, so we could have that. Then, what about a probability mass function? You need to know that too. Probability mass function is a probability function for a discrete random variable. Discrete random variable, say, we may call it x, where x can take values, okay, take values from, so 0 to infinity. All right, so x is an interval here in the real line. Okay, interval, well, we may say interval from the set of real numbers, that is from negative infinity. I think I'll just write that here. That will make it much more better. Okay. From negative infinity okay, write that. That is, I think I need the word from here. from minus infinity has to be black. Okay, from minus infinity to plus infinity. So we may just leave it like this for now. All right, so those are definitions, but then it leaves us with two other things that we need to know. The first thing is, what is a random variable? So a random variable defined before is a random variable, all right? A random variable is a mapping. A random variable is a mapping from the range, okay, from the sample space to the set of real numbers. All right, so a random variable is a mapping from the sample space to the set of real numbers. That's that about a random variable. We may also consider what a continuous random variable is. We need to know that. All right, a continuous random variable, a continuous random variable is a random variable that takes its values as is a random variable, we may say takes its values in interval form. All right, so actually what we are trying to say is that a continuous random variable does not take single values. So it doesn't take point values. That's what I mean. It considers the values within an interval. So, and when it's going to do, for instance, let's look at something here. If we want to look at the age of people now, the ages of people, I think coming from the standpoint of continuous variable, don't put the word random yet, so you can see something there. The age of people will usually be counting every time, every minute, every second, every hour, every day, every week. For instance, somebody says, I'm 20 years old today. In the morning, he was 20 years, maybe 20 years and 5 seconds old. In the afternoon, he's 20 years and perhaps 7 hours old. And later on, a few minutes later, he's 20 years, 7 hours and perhaps 40 minutes old. And the thing continues that way. So it's a continuous variable. All right. So bringing it to continuous random variable now, there are so many values that it can take. So we cannot consider, for instance, the ages of, maybe we want to talk about age of people now, and we have so many possibilities when we consider the age of people. So if we put the minute and hour and the minute and seconds stuff like in decimal, but the hours, minutes, seconds, and the others in decimal, and just the years in whole number, then it means we are going to have people having ages of maybe 1 year, 0.23, 1 year, so there's 1.23, 1.4, 1.5, 20.7, 20.78. So looking at that, we can cover every possible age that you may think of. So what do? We can only consider that in an interval form. And that is why we are looking at a continuous random variable. as a random variable that takes its values in interval form. So that's just that. All right. So then we can consider a discrete random variable now. What then is a discrete random variable? A discrete random variable is a random variable that takes its values. Okay, yeah, I needed to add something. Okay, I need to add something here. That takes its values in interval form, the continuous random variable now, from the real line or the set of real numbers. So we are considering set of real numbers here. Right. Whereas the discrete random variable is a random variable that takes its value, okay, from the set of natural, okay, counting, we could use the word counting numbers. So that you start from 0, 1, then you continue till infinity. So let's say that is from 1 to plus infinity. All right. So that's the discrete random variable. Let's give an instance. You know, when you start counting, you say, I have maybe no bag, I have one bag, I have two bags, I have 3 bags, I have 4 bags, I have 5 bags. Now, what are you doing here? What you are trying to do is say, I have this number of bags, I have that number of bags, and I'm doing fine. All right. So, but you are counting, nonetheless. You're counting. So what you may say, I have 2 cars, I have 3 cars, I have 4 cars, I have 1 phone, I have 2 phones, I have 1 computer, I have 2 computers. You cannot come and say, okay, you can even talk about human beings. I have 2 students, I have 3 students, but you cannot say I have 1.2 students, I have 1.3 students. That's not possible. So these examples are discrete. Okay, you may talk about many other things, but going back to the continuous variable, you could actually say I have 1.5, 1.5. Okay, let's say I have a gold of maybe that weighs 1.5 pounds. I'm just saying that anyway. So you could say I have a temperature, okay, this place has a temperature of maybe 32.73 degrees. That's continuous also. You could talk about the height of a person, maybe 1.68 meter. That's possible. You may talk about the voltage in a place, the potential difference. You may talk about maybe 1.9999 volts, like that, and so many other ones. So those are continuous random variables, but rather continuous variables. But when you say random variable, continuous random variables, it means that you are going to do a random experiment, and there should be some possible values that random variable can assume. So in the case of a continuous random variable, there are so many that we cannot list all of them. And so what we do is to consider the intervals. That's what we talked about the other time. So when I said interval from the set of real numbers, I meant to say something like minus infinity. All right. So that is here. That is from minus infinity to infinity. So in other words, we could write it like we could write it as minus infinity to positive infinity. All right, so that way we have what we are looking at. So now, having the knowledge of this, we may now go further to talk about what we really meant by probability mass function. Now, looking at this, well, you find out that the probability mass function belongs to a random variable that is discrete. So I'm talking about this. When the random variable is discrete, okay, we could just look at it from here. So when the random variable is discrete, we talk about probability mass function. When the random variable is continuous, we talk about a probability density function. So this and this. All right. Now, so that's that about that. So what do we really mean? I said something earlier about the probability function being a mathematical expression that can give the corresponding probability for each possible outcome of a random experiment. So when the probability function is actually for a continuous distribution, we call it a probability density function, a continuous random variable rather. When the probability function is for a continuous random variable, we say that it is a probability function. So I say it again. When the probability function is for a continuous random variable, we call it a probability density function. But when the probability function is for a discrete random variable, we call it a probability mass function. So that's the difference between the two. All right, now looking at this, why are we looking for a probability function, whether a mass function or a density function? We are doing this because we talked about a mathematical expression that can give the corresponding probability for each possible outcome of a random experiment. So we don't need to write everything down, we just need a mathematical expression so that when we specify a particular outcome and say we want the probability for this outcome, the mathematical function will give us that. So that's what we are trying to do. All right. Now, so in that case, we can go ahead. Now, what are the properties of a probability mass function? We start with that. So a probability mass function has the following properties. Okay, I think we may write 0, number 1. 0 is less than or equal to probability of x, and the probability of x is less than or equal to 1 for every x. All right, so that's the first property. The second one, summation xi. Okay, and we may just have x put here, xi. If you like, and I like it that way, I'll write range space of x. So just sorry. So let's have it as Rx, R subscript x. You have P, then you have Xi. Otherwise, you may just write I here, just put I instead of Rx. That's the range space of x. Then number 3, you have it that the probability of any event E is equal to the summation range space of x is an element. So everything in the range space of x that's an element of event E, and then you have probability of xi. So you're summing over this. So that's the third property. All right. Now, so the first property says that all probability values will be between 0 and 1, 0 and 1 inclusive. So they can be 0, they can be 1, or they just stay in between, but not outside the boundary. So probability values cannot be negative for a mass function. So I'm talking about properties of the probability mass function. All right, just make it a bit bigger. All right, so that's that. Property 2 tells us that the sum of all probabilities must be equal to 1. So if you sum, when you use your probability mass function, you get something. So your probability mass function is actually P of X, and then so let's say P of X. For instance, in the case of a binomial distribution, your P of X is going to be something like n combination x, p raised to the power of x, 1 minus p raised to the power of n minus x. So, and then x itself will take value from 0 to infinity. So from 0, but permit me, don't usually write it this way, but okay, I'll write in the way it's usually written. X equals to 0, 1, dot, all right, so n, so where it stops. Now this is it. When you have this kind of distribution, we are saying that this is a probability mass function, so you could just give a value of x and then you have your probability value. So when you have probability values for all possible outcomes, these are the outcomes, then you are going to, if you sum everything, you should get a value of 1. That's what we are talking about here. All right, so property 3, the last property, now says that if you want to find the probability of a particular event, then you just need to sum all the range, the space, okay, the values of the random variable that are involved in that particular event. So when you do that, you are going to get your answer. If that's not clear, that will get clearer later on in the course. Okay, you get clearer later on in the course. That's that about that. Okay, so what are the those are the properties of a mass function, but what is a mass function in itself? I've given an idea from what I wrote before, but let's assume a mass function we're talking about now. Let's assume that we write something like I wrote before, P of X. Now, while we're writing P of X, we may even say P of Xi. So, but in another way, to make it easier, we may write P of X equal to capital X now, this time around, equal to small x. And now, the capital X is the random variable itself. The small x is the value that the random variable takes. So, if we have this, and that becomes equal to probability of small x, note because of, we may put I here, so just to help the equation a bit. All right, so if we do that, if x can take values, let's assume that I itself, okay, so that we have x1, x2, so it means that I equals to maybe 1, 2, 3, like that, until we get to maybe xn. And then for each of them, there's a corresponding probability, p1, p2, and then until you get to pn. Then it means that we can actually have a probability mass function. So because we're having point values, don't forget that we talked about a probability mass function as a function that has that takes values that from the real line now, but takes them in such a way that they are count numbers like 0, 1, 2, thereabout. So it's taking values like that here, not taking an interval. And so that means we have a probability mass function. I've given an idea on it. If you remember that of, okay, yeah, okay. I'll give an idea on that now. So you remember that of the binomial distribution I talked about the other time is an example. So, but I will not give the binomial expression in full. Now just give an idea of what we can have. Suppose I toss a coin once. You know the sample space should be something like, no, a fair coin 2 times. You know the sample space should be something like HH, HT, TH, and then HH. Oh, sorry, TT, tail, tail. All right. Now, actually, we could have X taking values. So count the number of heads. We could have 0 heads. Supposing X is the number of heads that show up. 1 head. We could also have 2 heads. And if we do that, then we could have probability of these X's that we are having here. So if we have the probabilities here, so let's just call this probability of X, then we would have probability, in this case, we would have 1/4, because we found no head once, in which is this. We found 1 head 2 times. So this one will be 1/4. 1 head will be 2/4. And then finally 2 heads. We found that once here. So that will be 1/4. All right, so that's that. And since that has been covered, now we have a probability mass function, but this is not the function itself. This is just a probability distribution table, a probability distribution table. So the probability mass function itself is the distribution of a discrete random variable. The probability mass function is a mathematical expression that shows the probability distribution, okay, or gives that is capable of giving the probability distribution. So that's the probability mass function. You may call it the probability distribution anyway, but it is not a table. It's a mathematical expression that gives us that distribution itself. It gives us this distribution that we have in the table. So, but when the distribution is put in a tabular form, we call it a probability density, or rather probability distribution table. If it is actually written, perhaps, okay, if it's written in a mathematical form, then we call it a probability function. All right, so that's that about that. I think it's sufficient to call this a